All right. Well, I'll begin with a word of prayer. It's more or less time. It's time. Heavenly Father, we thank you for this day. We just ask you to guide our steps today. Help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, I think first order of business, I'm going to take off my shoes so that they can dry out. If you guys don't mind, feel free. Oh, the floor is kind of cold. All right. Aw, man, did I not bring my... Seriously? Do you guys see a bag anywhere? Nope. Let me phone a friend. So you guys have any questions while I'm arranging for markers to be delivered?
I've been so behind on homework. I'm going to start at 10.
I have a few markers over here. They're kind of sad, but... Well, what's the point of paying for a cell phone if they won't pick it up, you know? All right, let's see. Here's so, your parents ever told you that? I don't know. You're like, I pay for my own cell phone. Fair enough. All right. So let's get to it. I will lecture until this marker runs out, and then I'm going to get another one. So I wanted to talk about the theory of inverses, and I'm talking about inverse matrices, all right? So here's the deal. If A is an n by n matrix, and there exists B, another n by n matrix, such that A times B is equal to I, and B times A is equal to I, then we say A inverse is equal to B, and this is called the inverse matrix, all right? In this case, the matrix is said to be invertible, all right? So there's a few just theorems I need to prove about these sorts of matrices. So the first of which, theorem, oh, this one's nice, good. AX is equal to 0 if and only if x equals to 0 for, my bad, preamble here. Let A be an n by n matrix, right? Then AX equals to 0 if and only if x equals to 0. This business right here is equivalent to A inverse exists. So the existence of the inverse matrix, all right, is actually, you could add another date for me. That'd be awesome. Thanks. The existence of the inverse matrix is equivalent to the fact that the zero, like the homogeneous equation, has only the zero solution. All right? And I think the proof of this is instructive, so let's look at it. So this is a biconditional proof, so we're going to assume, not that I'm, okay, so like, let us, actually this way is easier. So let's assume A inverse exists, right? Suppose AX is equal to 0. That's true if and only if what? That would be interchangeable with, we can multiply the equation on the left by A inverse, right? So this would be interchangeable with A inverse AX equal to A inverse times 0, right? But what's that interchangeable? What can we go from there? A inverse is what? It's the identity matrix, right? So you got yourself the identity matrix here, right? And over here, what's this? This is 0. Any matrix times 0 is, right? So we have the identity matrix times x. So what we have then is x equals to 0. So this shows you that if the inverse, if the inverse exists, then the only solution to the homogeneous equation is simply the 0 solution. Simple as that, all right? The other direction, though, is a little bit more troublesome, all right? So suppose AX equals to 0 if and only if x equals to 0, right? Then what can you tell me about row reduction? The reduced to echelon form, right, of A with 0 slapped onto it has to be what? What does it mean to say 0 is the only solution? It means when we do the reduced to echelon form, right, we have to get what? 1's down the diagonal and 0, right? Because that's what it means to have the 0 solution and only the 0 solution. That means that every column in this n by n matrix, a pivot column, like that, right? But what does this mean? Because of the structure of row reduction, this implies that the reduced to echelon form of A is equal to the identity matrix, right? That tells us that the reduced row echelon form of A is itself the identity matrix, remember, because row reduction does what? It goes column by column, right? So I can strip off the 0 here, and it gives me that. But what did we learn about elementary matrices? We learned that there exists a product of elementary matrices, elementary E1, E2, EK, elementary matrices. Elementary matrices such that what? E equals to the product of, EK all the way down to E2 times E1, right? Such that what? Such that E times A is equal to the reduced to echelon form of A, but that's equal to I, right? So what does this mean? This means that the elementary matrix plays the role that it needs to be the inverse matrix for A, right? Do you see that? Not the elementary matrix, but the product of the elementary matrices. So like here, see up here, we need these two, we need AB equals to I and BA equals to I, right? So notice compare, right? This and that. So we already have this one. What remains in order to prove that A has an inverse? We still need to show what? The other, we need to show this condition, right? So how are we going to do that? So what I would do is, let's see here. I want to verify that my suspicion is that if I multiply E on the other side, right, we should also be able to simplify it to the identity, right? So let's consider A times E. Our goal is to show that that has to be equal to the identity matrix. Thank you, sir. I feel like I've worked myself into a corner at this point. I may be neglecting a previous proposition. No. Let's see here. Oh, okay. So I need to, let's not do that actually. Let's, I don't know how to, at where I am right now, I can't really make progress on that, so let's not do that. But what we can do is we can take the equation we already have and rewrite it more explicitly. Like this is, you know, EK times dot 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 E2, E1 times A equals to the identity matrix, right? And the thing is, we already know that every one of these elementary matrices is invertible by our previous discussion. So what that means then is I can solve this by multiplication of, like I can multiply by EK inverse on the right, and then all the way on down to E2 inverse and E1 inverse times my, oh man, sorry guys, I gotta flip the script on that. We're gonna do EK first, EK inverse first, then EK minus 1, all the way on down to E1 inverse, that, right, that times what's given. See, I need the EK to come first because that comes first, right? So in order to get them to cancel, I have to multiply them in the reverse order. But on the flip side, we've got E1 inverse, E2 inverse, EK inverse. All right, fine. So if I do that, and I can do that because every elementary matrix is also an elementary, its inverse is also an elementary matrix of the reverse row operation, basically. What happens here? You see? We kind of talked about this the other day, but this is, you know, these guys, they all give you the identity matrix, right? So you get identity times identity, you know, this becomes simply the identity matrix times A. So this calculation shows us that A is equal to, actually, E1 inverse, E2 inverse, dot, 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 EK inverse, right? Which, by the way, we explained the other day that this is actually E inverse, right? That is nothing more than the elementary matrix, the product of the elementary matrices inverse, right? So what does this all mean? Well, hence, if we look at AE, right, instead of EA, what does that give us? Well, that gives us E inverse E, which gives us I. So now I have shown that the matrix E satisfies both the equation AB equals to I and BA equals to I. Thus, A inverse, in fact, is equal to E. So we had some information about the invertibility of elementary matrices before today. It turns out that information is contagious. All right, basically it spreads to every matrix in this way. Okay, so there's more that we can see from this proof if you take a look at it. So what could we add to this litany of equivalence? Only the zero solution exists. The inverse exists. That's what this argument shows. All right. I don't expect you to be able to like reprove this. This is not a proofs class. This is for your information, but I do expect you to know this conceptually. Like the theorem, you need to know and be able to apply. The proof, if you understand it more deeply, right? But you don't have to understand the proof necessarily. But you do need to know this result. And we can add more to this, all right? We can add more because we can say this is true if and only if A is what? A is a product of what? What kind of matrices? True, but there's a special kind of matrix, not just any matrix. This formula right here. What's this show you? It's a product of elementary matrices because every one of the inverse of an elementary matrix is again an elementary matrix. So if A is a product of elementary matrices. But there's more because once you know that, you see that we don't need both conditions. All right? Actually, this is true if and only if, like, there exists B, in n by n, such that BA is equal to I. And I can add it up here. There exists B in our n by n such that AB is equal to I. This is wonderful because going forward, we don't have to check both AB equals to I and BA equals to I to have an inverse. If you have either one of those, it follows that you have the other. That's the structure here. Right? So there's that. Now, I got to be careful not to step in the drops, otherwise it'll be counterproductive to my project of drying my feet. All right, so so we have what? 1, 2, 3, 4, 5 characterizations of invertibility of a matrix. Are there others? If you look at Anton's calculus, he has this, not calculus, linear algebra. He has this like growing list of equivalent characterizations of invertibility of a matrix. By the end of the book, I think the list has like 20 things. All right, so there's like so many different ways we can look at invertibility of a matrix. We're just getting started. So this is by no means not done. But another thing to think about is solving multiple systems at once, right? So you've had a homework problem on this, right? Where I was just hoping you can discover it by looking at patterns for the row reduction, right? But now we can do better. We can derive how we solve multiple systems at once using elementary matrices and such. So check this out. If I have A, I'm trying to solve like AX equals to B1. And I'm also trying to solve, say, AY equals to B2. Suppose I'm trying to solve both of these systems at the same time. All right? But they've got the same, the same coefficient matrix, right? So what would you do? You can solve this by looking at what? Roof of the concatenation of A with B1, right? And that's going to be what? That's going to be E times AB1, right? Likewise, over here, roof of AB2, you're going to calculate some row reduction, and at the end of the game, it is an product of elementary matrices times the augmented coefficient matrix of A with B2, right? But notice that because the first columns, right, are the same, the row reduction is the same in this case. Adding a column, right, does not change the row reduction. They're both bound by the same set of elementary matrix operations. You saw that in the homework exercise, but now I'm telling you we can understand it in terms of a product of elementary matrices. But then what? But then notice that if you can put these two together. You can put these two together, you see? Because if we have E times like A with B1 and then B2, like this, all right? So here, I guess to be clear, I'm assuming for the sake of this discussion that A is like a square matrix, but I mean, truthfully, this still works for rectangular matrices, but for the sake of simplicity of discussion, let's suppose A is a square matrix, right? So we've got like n equations and n unknowns, but we got two systems of n equations and n unknowns. So that would make A like an n by n, and these would both be n vectors, right? So you got what, like an n by n plus 2, I think? N plus 2 columns, yeah? Well, then there was a rule of matrix multiplication, the column by column rule, which said that this is EA, EB1, EB2, right? But this is actually the reduced row echelon form of A with EB1 and EB2, right? And on the other hand, this is the reduced row echelon form of this matrix. But if you go back up to here, you see this is actually the same, by the same identity. This is EA with EB1. And this is EA with EB2. So you can read off the solutions to a pair of systems by simply examining the last two columns and ignoring, like, so to solve, you know, AX equal to B1, I can just look at this and that tells me the solution, right? If I want to solve AX equals to B2, I look at this and that, and it tells me the solution, right? For example, if I knew that I had, say, a system whose reduced row echelon form had the form 1, 2, 0, 0, 0, 1, 0, 0, 0. I'll put a minus on this too here for fun. And then I've got, 7, 8, 0, and I've also got 1, well, I guess I've got 0, 0, 1. Suppose that's the situation, right? From that one row reduction, I can read off solutions to two systems of equations, right? If this is x, and this is y, and this is z, I can tell you that, x minus 2y plus, I'm sorry, I haven't given you the original system. Rats. Well, I'm sorry, guys. Let me fix this. I meant to say that this is equal to. I'm like, what's the system? Well, I'm just writing down the reduced system, which is dumb. So here we got A with B1, B2, all right? So A with B1 and B2, suppose it simplifies like that, all right? And I'm supposing the system of equations, has variables x, y, and z. So on the one hand, I have, I shouldn't use x, y, and z, should I? What should I use? I used x and y as like vectors up here, so let me use something else down here. What do you guys want me to make the variables? Student's choice. What do you want the variables to be named?
P, Y, and K.
P, Y, and K. Y is, we can't do Y. Y is off the table. What's that? V or phi? Did I hear phi? I'll take a phi. P, phi, and K. All right. That's odd, but I'll allow it. So.
Frat row of the matrix.
All right. So AX equals to B1 has solution what? It is equivalent to saying P minus 2 phi apparently is equal to 7. And also K is equal to 8. That would be the solution to AX equal to B1, given that information, would be given to us by P minus 2 phi equals to 7 and K equals to 8. What am I looking at? I'm simply looking at the first 4 columns, right? On the flip side, if we look at AX equals to B2, this is equivalent to, well, I guess this, P minus 2 phi equals to 0 and K equals to 0, but most interestingly, the last equation, this one right here, right? That's a problem, right? So that shows you that the system AX equals to B2 is in fact inconsistent. All right? Does that make sense? So we can solve more than one system at a time. Now, why does this matter? Now, I showed this for 2, but we could just as well do this for k systems at once, right? You could do this for more than 2. You could do it for 3 or 4, whatever. So let's talk about the problem of calculating the inverse. Right? Let's talk about that. So let's let A inverse equals to V1, V2, Vn. We'd like to find these, all right? Let's let V1, V2, all the way out through Vn be the columns of the inverse matrix that we'd like to find, right? So let's talk about this. What is, how can you understand these in terms of an equation? Well, notice that we have to have, by assumption, A times A inverse is equal to the identity matrix, right? That is the defining condition, as it happens, right, for the inverse matrix. You're like, well, you also said that you have to have A inverse times A equals to I. That's true, I did say that, but we just got rid of that. Started today, right? So that's enough. If I can solve that, I have found the inverse. What is the identity matrix in terms of the standard basis? This is E1, E2, En, right? Remember what the E's are? These are matrices, vectors that only have a 1. E sub I is the column vector, which has a 0 in every spot except for the ith spot where it has a 1, right? Okay, so what is this? Well, this is A times V1, V2, Vn equals to E1, E2, En. But we know the column by column matrix multiplication rule, right? Which says what? It says that this is actually equal to AV1, AV2, AVN. So all of a sudden, you see the problem of finding the inverse matrix is actually the problem of solving n equations with n unknowns n times. N equations with n unknowns n times. In particular, we have to solve A times Vj, is equal to Ej for j equals to 1, 2, n. But how do you solve a bunch of equations all at once that all have the same coefficient matrix? Well, we know how. We just learned in example 1 and this discussion. I did it for 2, but guess what? You can do it for n just the same. And so the answer is, to solve all of these equations at once, all we have to do is what? So we just need to calculate what's the reduced row echelon form of like A with what? These are my inhomogeneous terms, right? The standard basis is the B's I'm trying to solve for. So I've got like, my first one is E1, my second one's E2, and so forth and so on, all the way out on En, right? And in other words, we're trying to calculate the reduced row echelon form of the matrix concatenated with, what is this? What is all this? That is the identity matrix, right? And so we have the following theorem. If the reduced row echelon form of A with the identity matrix concatenated is equal to the identity matrix with some matrix B over here, then A inverse is equal to B. If the reduced row echelon form of A with the identity matrix concatenated is not equal to the identity matrix with some other matrix over here, let's call it M, then A inverse does not exist. my second point there in the theorem follows from the fact that if you did the reduced to echelon form of A, and you didn't get the identity matrix in that first block, what that means is that A is not actually a product of elementary matrices. Let's see here. All right. Any questions while I'm trying to make sure I'm not missing something here? I know one thing I'm missing, so I'll get to that, but. Let's see here. So, like example 2. Suppose we have A equals to 1, 2, 2, 4, right? Let's calculate the reduced row echelon form of A with the identity matrix concatenated. So we're trying to. So we need to look at what? 1, 2, 2, 4, 1, 0, 0, 1. What's that give us? We got row 2 minus 2 row 1. What do we got? Man, I thought I put my markers in my bag. This is really weirding me out. Huh. Did I ever? I walked back here to move the camera already, didn't I? Like, I did? You moved it. Oh, okay. This is very disconcerting. Thank you. Thank you. Much appreciated. So what's that give me? We got 1, 2, 1, 0 up here. And down here we got what? 0. Then what? 0. Oh. Oh. Negative 2 and 1. And then, let's see here. Let's see. Then I can do what? This is row 1 plus 1/2 row 2, right? This gives me what? It gives me 1, 2, 0, 0, and then 0, minus 2, 1, and I guess this is a half. And then finishing below, row 2 divided by minus 2. 1, 2, 0, 1/2, 0, 0, 1, minus 1/2, right? So what does this mean? If you believe the theorem over here, this says what? Does A inverse exist? So this right here is the reduced row echelon form of A with identity, right? As you can see, this is not equal to the 2 by 2 identity, right? So therefore, A inverse does not exist. All right? Why is that? Why does A inverse not exist here? Is there another way we could look at the non-existence of a matrix, by the way? For the 2 by 2, there's another way, right? What's the way we can calculate the inverse of a 2 by 2? I told you guys, like, I think Monday. What's the formula for the inverse of a 2 by 2? Remember? We learned A, B, C, D. Inverse is what? It was 1 over AD minus BC. You know, flip the diagonals, minuses on the off diagonals, like that. So for my matrix here, if I've got 1, 2, 2, 4, inverse, I get what? 1 over 4 minus, oops. 1 over 4 minus 4, that's a problem. right? Does not exist, right? So actually, good news, our 2 by 2 inverse formula will verify what the theorem says, right? And for a 2 by 2 matrix, by the way, this is the way to do it, right? This is very cumbersome. But for a larger matrix, we pretty much have to use row reduction to calculate the inverse, all right? So how about the remark? Let me make a remark here. Columns of A here are linearly what? Blank. Are they linearly independent? Are they linearly dependent? What do you think?
Linearly dependent.
They're linearly dependent, right? It's kind of obvious, right? Like, why? Why do I say that? You got what? Column 2 is twice column 1, right? One's a scalar multiple of the other, like we talked about last time. That gives linear dependence. Check this out. Theorem. A is invertible if and only if the columns of A are linearly independent. Here's yet another one we could add to our list. This is very easy to prove. How do you characterize linear independence of the columns of A? What's that mean? That means that if we have a sum, right? Say I equals 1 to x, n rather, of let's say x sub I, column I of A equals to 0, that has to imply what? So this is a linear combination of the columns of A. If the columns are linearly independent, what does this have to imply about the coefficients x sub I? They have to be 0, right? In fact, if you think about this, we can put a double arrow here, right? Like linear independence gives me this implication, but the other implication is just a fact of algebra. If these are 0, that's 0, right? So I can make this go both ways, right? But this, my friends, is nothing more than the matrix equation AX equals to 0. With x being x1 through xn, because AX is a linear combination of columns of A. So to say AX equal to 0 has only the 0 solution is to say that the columns of A are linearly independent. Which means, by our theorem to start of today, that A inverses exists if and only if the columns of A are linearly independent. This is very helpful. It saves you a bunch of calculation for like non-examples. Here's another one. See, if I say A is equal to 1, 2, 3, 1, 0, minus 1, and then let us say 2, 2, 2. Uh-oh. We don't have to leave, do we? No. Okay, it's good. It's all good. I have another student who's got like a pencil sharpener she keeps using in class. It's very disconcerting because I'm not expecting you to. It is Heidi. Whoa. See, that's how special it is, right? Yeah. I like Heidi. But anyway, so here we have column 1 of A plus column 2 of A is equal to, this is like the only example I have, right? Column 3 is what? Right? So this is column 3. So what does that say about this matrix? This right here shows you columns of A are what? Not linearly independent, right? Why do I say not linearly independent? Because that's easier to write than linearly dependent. We don't have an abbreviation for linearly dependent typically, so whatever.
Not LD.
Yeah, we just don't do it. I don't know why. I don't know why. It's just, you know, no one says LD. I mean, you can be the first, you can be a trendsetter. You can do it if you want. I don't refuse you guys the ability to make up an abbreviation and use it on your test if you want. Fine, like whatever. But the point is that the columns of A are not linearly independent. Therefore, A inverse does not exist, right? And that can save me a whole lot of calculation, because actually calculating the reduced row echelon form of a 3 by 3 matrix, slapping the identity on, well, that's kind of a pain, right? All right. So another example I wanted to show you guys, I need to get the projector out here. Oh, before I forget, what are the properties of invertible matrices? I think I told you most of these already, but so the one we talked about already, like sock shoes, AB inverse is B inverse A inverse. I think the one I forgot to tell you is like if I've got a constant times an invertible matrix, it's 1 over the constant times the inverse matrix. So these are two big properties of invertible matrices, the sock shoes and also if you've got a constant, you just reciprocate the constant. So, all right. Come on. Computer, come back to life. Thank you. So while we're waiting for my computer to behave, question for you guys. You've got n equations and n unknowns. Ax equals to b, right? If A is invertible, can you solve it? You can. Is there a unique solution? Yes, there is. What is that unique solution? I got too many tabs open. I'll eventually find what I'm looking for. Oh, here it is. All right. It's the elementary matrix, but let me be more explicit. So to like, if we know A is invertible, right, and I'm up against the equation Ax equals to b, what is the solution? There's only one, the unique solution. I take this equation, and I multiply by the inverse. You see? This implies that A inverse Ax is equal to A inverse B, right? But A times A inverse is the identity matrix, so we get identity matrix times X equals to A inverse B, which gives us X is equal to A inverse B. So in the case that our n equations and n unknowns has an invertible coefficient matrix, the solution exists, and it's unique. All right? On the other hand, if I gave you the information that Ax equals to b has a unique solution for every possible b, that also tells you that the inverse exists, because what you can do is you can take b equals to e1, e2, all the way out to en, right? And solving Ax equal, AV1, AVI equals to EI, for I equals to 1 to n, amounts to finding the columns of the inverse matrix, right? So if I knew that Ax equals to b has a solution for every b, then I also have the invertibility of A. There's the whole family of interconnected ideas here, all right? One of those is that if you have n equations and n unknowns, and you don't have a unique solution, right? If there's more than one solution, that means that your coefficient matrix is not invertible. If you think about how this all works, that makes sense, because the row reduction of such a matrix will not be the identity matrix. It's going to have a non-pivot column, right? Which is to say that the row reduction of A with, the inhomogeneous terms, it's not going to just be the identity matrix. And that means it's not invertible. All right. This is an example that I probably should have showed you like Monday. I'm sorry, guys, but here it is. So sorry, it's a little fuzzy, but this is a nice example. Unfortunately, I really like your book that I'm not really talking much about, but it is a good book. And if you want to get extra practice beyond the homework that I've assigned you, looking at, the book that's the required book for this course would not be a bad idea. I mean, the homework I assigned you guys to turn in is not really expansive, right? It's like a minimal homework set. It's by no means like enough for everybody to get where they need to have mastery of the material by any means. It's kind of like a just entry level understanding the homework in here, I think. There's not, what I'm trying to say is there's not a lot of it. If you're in my differential equations right now, I wouldn't say that. In my differential equations right now, they're suffering through a much higher level of homework. I was unsatisfied with differential equations last semester, so I decided to turn up the heat on the frogs in the pot. They're not jumping out yet though, so it's okay. But none of you are in there, right? So tell no one. It's okay. There's no record of this, right? You were in last semester, so you got the easy semester. Let's see here. So
I was in disappointment semester.
Yes. Well, I'm disappointed in myself for not assigning more homework, because as I look back at the dozen times I've taught differential equations, I could do better than last semester. So anyway, but which isn't to say I didn't teach anything in your course. Obviously, you suffered through it. But so here's a chemical reaction. Don't ask me for the names. HCl plus sodium something or other. Any chemists in here? I know the Na is sodium. I think that's sodium. So this is like 3 sodiums, and I think that's here's the words. Hydrochloric acid plus sodium phosphate. It goes to phosphoric acid plus sodium chloride. So what's going on here? Of course, in a chemical reaction, right? You don't lose molecules, right? Like if you've got 10 hydrogens coming in, you got 10 hydrogens going out, right? How do you change hydrogen to something else? That's not chemistry, that's nuclear physics, right? To change the atomic number, you have to have some sort of radioactive decay. This is just plain old chemistry, there's none of that. So the kinds of molecules coming in and out, or rather the kinds of elements coming in and out are the same. So if you keep track of all the different elements involved, hydrogen, chlorine, sodium, phosphorus, and oxygen, you see that each one of these molecules, right, which is made from putting together different elements, corresponds to a particular vector in this, x1, x2, x3, x4 space, where we're using x1 for sorry, come on. Oh, so let me add some value here. So you guys tell me, what's HCl as a vector? I guess we're using hydrogen, chlorine, sodium, oxygen here. So I think HCl would be like a what? 1 hydrogen, right? 1 chlorine. Oh, come on. Then what? So just 1 hydrogen, 1 chlorine. Any sodium, phosphorus? No. So 0, 0, 0, right? So that's the first thing. The sodium phosphate, how many hydrogens are in that? None, right? How many chlorines? None. How many, good grief, what's the next thing? Sodium. How many, there's 3 of those, right? And then how many, whatever that is, phosphate? Potassium, right?
That's phosphorus.
Phosphorus. Oh, that's phosphorus. So one phosphorus and then what? 4 oxygens, right? So if I'm not messing this up, I think that gives us this vector. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And that equals what? Like x3. hydrogen, we got 3 of them. We got no chlorines. We've got, was P the middle one? It's one of those. Which, so was sodium 3?
Yeah, there's no.
Oh, so there's no sodium. There's 1 P and 4 O's. All right. X4. We have no hydrogens. We've got no chlorines. We've got 1 sodium. Oh, we got 1 chlorine. So 0, 1, 0. So if you look at this, we have to choose x1, x2, x3, and x4 to balance these equations, right? And so when you look at these equations, you see what you got. X1 is equal to 3x3. See that? X1 is equal to x4. X2, 3x2 is equal to x4. See where these are coming from? It's just that. And I think this is actually kind of an interesting system of equations because these typically will have, oh man, they'll have infinitely many solutions, but they are by very much of course, a physical example. But anyway, that's it for today, guys. Have a good weekend. I'll collect the mission, I think, next class. So.